I would like to address the implementation challenge and provide some update in the spectrum regulation about this regarding the latest development, as well as some of the enabling technologies for FR3 base station. So this is my talk agenda. First, I will provide the spectrum update, and then I will walk through some of the foreseeable implementation challenges for this new frequency and the opportunities for the industries to work on, primarily focusing on the semiconductor industry. And then I will conclude my talk. So why do we need 6G? And since we already have 5G, but as we probably know, since one big problem is the foreseeable data explosion. So since we move from 3G to 4G, according to for example, the Ericsson mobile report, and you can find this trend in many other reports, the data just exploded. And this cannot be sustained with the current network technologies. Therefore, a new technology such as 6G has to be introduced to support the capacity demand. And how can we achieve that? First, you can, of course, go to new frequency band to look for wider spectrums. Can help you to increase the capacity. Another way is you go to improve the spectrum efficiency, so you can pack more bits within the same spectrum. And in addition to that, you can also densify your base stations or introducing other beamforming technologies will increase the set densities. So by combining these technologies, we hope to overcome the capacity data load challenge to make the future network support the consumers and industrial use. So what is FR3 band? FR3 band, we know the FR1 band currently, which is primarily up to sub-6 or sub-7 gigahertz, with the latest 3GPP introduction of some of the band, like band N104, is already touching the 7 gigahertz. And on the other hand of the spectrum, we have the so-called FR2 band, starting from 24 gigahertz to 39 gigahertz. The latest have FR2-1, FR2-2, defined in 3GPP. So this the so-called FR3 band actually is not yet a official name introduced by 3GPP, but people started calling this FR3. So the advantage is a best trade-off between the lower frequency and upper frequency. In the low band, we have very good coverage, but the spectrum is already very crowded. Therefore, at the beginning, we went to the FR2 band, where we have the millimeter wave as a chunk of easily available spectrums for us to use. However, so the FR2 band has its own limitations due to the higher frequency, such as the path loss and some other physical challenges. So this FR3 band sits right in the middle, namely between 7 gigahertz and 24 gigahertz. There are current already existing applications sitting in this FR3 band, including satellite communications, defense, radars. So if we would like to introduce a cellular band, it's also not an easy task. And you can foresee some of the licensed options on shared options of frequency use, reuse, refarming has to be introduced to support these initiatives. But nonetheless, it has already attracted considerable interest for this new frequency band. So here is a plot comparing the 5G and 6G, the so-called wedding cakes. And if you can see on the 5G case, the operators has to introduce the different layers of cakes for different use case, because different frequency band, you have different physical behaviors or characteristics. The higher frequency is good for high speed, high data rate, but has limited coverage. So when we move from 5G to 6G, the additional frequency band has to be introduced. On the right side, I listed some of the band of interest. For example, the sub-terahertz or around 100 gigahertz, which is providing extremely high data rate, but it may not be, it might be only used for very short range sensing applications or other communication applications. However, the talk of this is focused on FR3 band between 7 to 20 gigahertz. One of the foreseeable use cases, excuse me, is for the urban extremely capacities, meaning the deployment scenarios will be for the dense urban case where you have a high demand of capacity. So this is a nice chart from Nokia. Actually, it explains the different frequency starting from 1 gigahertz to 100 gigahertz. So the green areas listed some of the band which is currently discussed under the ITU and the 3GPPs as some of the study items to explore the channel characteristics. For example, the sub-terahertz I mentioned before. And on the left side, it actually mapping the optimum characteristics or use case and physics for this corresponding band. So as I mentioned before, the FR3 band, even though it's called 7 to 24 gigahertz, but as currently the industry is mainly focusing on the 7 to 15 gigahertz range, try to standardize these frequency options. So how do we, if we are going to deploy this FR3 band for base stations, and one of the challenge is for the operators certainly is to want to reduce the deployment cost while offering the best performance. So here is a chart comparing the existing C band or mid band 3.5 gigahertz and 7 gigahertz, 14 gigahertz, and 28 gigahertz. You can see if we target of SNR of about 0 dB, which is the typical numbers, and you listed the set coverage distance, it is possible, it is plausible to deploy at 14 gigahertz, for example, with about 260 meters distance. And the assumption made here is about 400 megahertz bandwidth and 200 watt power and 26 dBi base station, and then again, subject to the EIRP and the EMF FCC exclusion limits. And therefore, this study is also again from Nokia. The conclusion it is feasible to deploy the urban rooftop sets within this FR3 band, the lower part of the FR3 band. So regarding the spectrum deployment and options, this decision has been discussed later last year in December timeframes, held a long discussion in the ITU WRC World Radio Conference in Dubai. So the outcome of this conference regarding the 6G or the FR3 band is listed, is well summarized in this chart. According to different regions, you have the different outcomes given the deployment situations. For the C6G FR3 band, for example, 4.4 to 4.8 and 7.12 to 8.4 and 14 to 15 gigahertz are listed as a potential candidates. This is going to be studied between now and the next WRC 27 as study items. Hopefully, it will be approved by WRC 27 as a 6G official band in the FR3 region. Of course, in the different countries, such for example as the US, which is also exploring some of its different FR3 options, which is also listed here. You can see the US 6G on this chart, like for example 12.7 to 13.3, which even though is not a WRC conclusion, but it's also currently studied by the FCC, for example. So that was a spectrum of the candidate band. Regarding the timeline, maybe this chart give you a good informations within the 3GPP. one of the biggest events will be the 6G workshop is kicking off very soon in this year. And you have the different study phases to study this FR3 and other 6G technologies. And the timeline is targeted by release 21. You have the first 3GPP 6G spec. And the commercial deployment is planned right now at 2029. And that's the standardization part. In the ITU IMT, is 6G's officially name is called IMT 2030, similar to the previous generations. Those are the bands and agendas. As you can see, WRC 27 will make the new bands decisions. So that was the FR3 spectrum update part. And then I will dive into the implementation challenge and opportunities to design this kind of new radios. So if you compare the existing 5G KPIs and the 6G KPIs, for example, you can find many informations from different companies and research institutions. The conclusions, for example, you get sometimes about roughly 10x improvement depending on which metrics you're looking at. For example, the user data rate experience is again 10x improvement compared with 5G into 6G. And another important part is the spectrum efficiency has to be improved again. Of course, the energy efficiency is also important. So these are the envisioned 6G KPIs as we always experience from the previous generation as well. But how can we achieve and how can we make sure it's going to be successfully implemented in the 6G base stations? On the right side, you can see this axis, the y-axis shows the frequency. You have the current FR1 band and then the FR2 band and the 100 gigahertz. Sorry, there's a typo here. 100 gigahertz of the sub-terahertz. These are the different knobs or different technologies you can explore to support the KPIs. One of the interesting items I like to point it out here is you can see between the FR1 and FR2, in order to improve the spectrum efficiency capacity, the high rank small antenna is a very instrumental technologies and is very suitable at this band. What does that mean? It means the frequency characteristics of this FR3 band is very suitable to increase the antenna elements and the array size, and as a very good tools to improve the network performance. Because a low band antenna size is very big, and if your frequency is too high, then the channel is very challenging and very sparse. You cannot explore the MIMO or massive MIMO or multi-user MIMO's characteristics to improve the network capacities. Therefore, this is indeed considered as a sweet spot to explore the so-called extreme X MIMO, massive MIMO technologies. So what is massive MIMO or multi-user massive MIMOs? Why do we need that? How do we implement that? Well, what are the challenges here? So the left figure basically compares for different array configurations, which actually corresponding to different frequencies or different generations of the base stations. This would be the old days of 2G or 3G, as more or less of 4G applications. And these are the widely deployed massive MIMO in the current 5G case. So as you can see, when you make the improvement or design change on the antennas, active antennas panels, you will get extra of the beamforming gain. And when you further increase the number of antenna elements, active elements, you can have larger arrays. What does that mean? You can increase the digital pipes and also the radios, and therefore you can also have more flexibilities in terms of the beam control, interference management, and shape your beams targeting the user and support 2D, namely the horizontal and the vertical scannings to serve the user better and increase even also the cell coverage, which is very important. So what is behind this active antenna panels? So these are typical configurations of existing mid-band, for example, 3 gigahertz and also the FR2 28 gigahertz base station units. You had different layers of the signal processing. And for example, you have the baseband units and the high-speed interface connected with the active antenna panels. And there are some layers is responsible for beamforming, namely how do you steer in the beams. It can be done in digitally or can be done in analogically or can be a combination of both. And that you need a different SoCs or different front end to support these functionalities. And also very important is the analog front end, where you have the conventional analog chains, depending on the specific implementations and the architectural choices, the different analog components can be selected. So overall, you can see the higher performance of front-end technologies and advanced signal processing algorithms, naming the channel state feedback or beamforming coding books. All this can contribute to the improvement of the multi-user massive MIMO technology, which become a default choice. And also even for the passive design, the filter technologies, the antenna design using different materials with a lower loss can also contribute to the technology implementations. So this just shows a comparisons of how much capacities or how much spectrum efficiency. On the left side is basically we compare when you increase the bandwidth from 20 megahertz to 100 megahertz and to the for example further to 400 megahertz in the 4G and 5G and 6G, when you also reduce the radio pipes or how many, for example, the conventional right now the 5G is mainly using 32 TR or 64 TRs. And if we can further increase the radio channels to higher numbers and with expanded bandwidth, you can see the peak data rate of the cell can increase even to 16 gigabps for a cell. Which is how you increase the cells, as I mentioned before, to support the traffic. Another one is important on the spectrum efficiency. On the spectrum efficiency side, compare with the 5G massive MIMO choices, where for example, typical numbers of base station supporting 16 layers with 64 TRX. If we can double that numbers, or given the physical size limitation of the antenna arrays, if we can increase the radio numbers and we can further increase the massive MIMO spectrum efficiencies gained through the higher number of antennas and higher number of radios. And on the other side, if we also introduce the UE side, the improvement of the antennas and the improvement that can also further increase the spectrum efficiency, which is the most valuable parameters. So, but what are the good things here is when we go to higher frequency? For example, compare with the existing C-band 3.5 gigahertz. This is the typical antenna panels. You have columns, you have rows, and typically you have, for example, have a 64 teeth, and this would be the antenna elements. You have about 200 elements. We know that for the active antenna designs, the antenna element spacing normally is about half lambda spacing to properly design the beam shaping. So if we double the frequency band, if we increase the frequency from 3.4 to 3.5 to 7 gigahertz, then of course the wavelength reduced by half. And if you still use the same number of antennas, then your antenna panels is reduced. However, due to the frequency characteristics at higher frequency, the path loss increases. Therefore, you would have the challenge of reaching the same set distance. However, if we keep the same antenna panel size and if we double the frequency on the X, Y dimensions, then we can patch 2 times of the elements. That means the total antenna elements will be quadrupled. So therefore, we can pack, for example, about 768 antenna elements at 7 gigahertz without changing the antenna elements. So talking about FR3, which is, for example, about 15 gigahertz, there is again another double of 7 gigahertz. So it's again given the same physical size, again the antenna elements can be quadrupled, about maybe 3,000 or 4,000, depending on the trade-off you're making. So what is the message here is that if we go to higher frequency from the current C band to the FR3 band, we have the luxuries to pack more antenna elements and more radios without increasing antenna panels. Therefore, we can compensate the limitations introduced when we go to higher frequency. So of course, how do you really implement this or design the radio is many multiple choices or trade-offs you can make. If you want to increase larger arrays, these are the example given by these Ericsson white papers talking about the different options and different challenges. Of course, to design a bigger arrays, you can certainly increase the sub-array size. A sub-array is an array served by one radius unit, one radio pipe. If you increase the sub-array elements instead of, for example, three element sub-arrays, you can go to 6 or 8 further elements without increasing the active radio numbers. However, the limitation would be your beam becomes narrower and narrower. You may have some limitations. Or you can, without increasing the sub-array size, you can increase the actual radio ports numbers. But that comes with the limitations associated with the complexity and heat and cost challenge. I would say the right balance between the architectural choice will play a critical role when you're sizing the radio design. Therefore, you always strike for complexity and flexibility balance between that. Since in the previous generation, when we talk about the power consumption, we probably mainly think about how much amplifier power consumption is dominating. But since for those kind of base stations, massive MIMO, the actual numbers of the radio pipes becomes significant as well. Therefore, the associated baseband power consumption also becomes a significant portion. Therefore, we have to consider both the baseband or the baseband signal processing power consumption as well as the RF power consumptions. They do matter both. So another challenge, look at in specific our front end challenge. When we go to higher frequency, we know the efficiency of power amplifiers starts challenging when you go to the higher frequency. What that implies that given the smaller chip size, the heat dissipation becomes a critical challenge, as well as how do you do the integration, packaging, and fabrications, because those are contributing a big factor of the success of the network and from the hardware perspectives, right? But that's related with the cost and the reliabilities issues. So I would say these are the very critical physical challenges that we engineers have to work on to come up with innovative solutions to push the envelope of the technologies so that we can come up with a very small size or small footprint compact solutions to fit into these squares of the laminates. So as you can see before, the beamforming, probably this chart are well known for many of you, but let me just walk you through about the architectures, maybe for some of us are not less familiar. So digital beamforming offer you the highest flexibility. Why is that? Because as you can see, each antenna actually is connected with one complete digital and RF chains. You have the ultimate flexibilities in terms of designing the beam patterns and the controls and beam shaping and capacity and all that good things. But associated with, certainly you would have to pay this due to the high demand of the digital analog converters and as well as mixers and all that. RF chains has to be provided for the full digital beamforming if you want to do that. On the other extreme is you do the full analog beamforming, which is the most simplest beamforming I would say, but it's also widely used for the existing FR2 solutions, where you have the because of the bandwidth challenge at FR2, you would simplify the front end solutions, like you will feed the deck with only one deck and then divided the radio channels to do the beamforming at analog and mainly at RF frequency directly. So in between the full digital beamforming and analog beamforming, you would have a hybrid beamforming where you do not go the extremely case, rather you subdivided the antenna arrays into different sub arrays, and where each of them is fed by one digital streams. So this offers a good trade-offs between the flexibilities and the complexities and related again is a performance and the engineering challenges. So this table basically summarizes what I just explained in the previous chart. In terms of complexity, you can see hybrid beamforming sitting in the middle. In terms of the numbers of the analog components, is also a trade-off in between of digital and analog beamforming if you choose a hybrid beamforming. So even for talking about hybrid beamforming, you would again have a different implementations or challenge depending on the frequency and depending on the power levels. For example, this chart is showing you a hybrid beamforming, but it's implemented using a high power amplifiers. The advantage here is you can use a very high power amplifiers, which has a significant output power. I don't want to go to the detailed numbers, but you can assume you have a gallium nitride power amplifier, which is, for example, capable of offering a high power. And then since this is the high power output, then you can further, you have the possibility of feeding them with the different antennas and with enough TRP powers. So how to do the beamforming here? So one way of doing this is you introducing the phase shifter delay lines by the back-to-back switches. Then you can switch different physical lengths. Therefore, you can introducing the delay and you can shift, you can steering the beam, or you can form the beam as well. So this is so-called post-P beamforming architectures, where certainly the quality or insertion loss becomes every dB counts after the P, as we know that has to be as low as possible, and these things becomes very challenging to design a lower loss beamforming solutions. Therefore, on the other side, for example, one of the typical application is FR2 beamformings, where you have because of the limitation of the wavelengths, and it requires a chipsets, and we have to use a RF analog beamforming, and whereby the beamforming is actually introduced before the amplifiers using the beamforming elements, for example, phase shifters. These are the offering a very good trade-off of the challenge and the performance. This is so-called pre-beamforming. As we can see, the real architecture or the solution depending on many considerations, including the frequency characteristics and the performance requirement, the EIRP power requirement. At the end of the day, for this FR3 band, we would see due to the higher amount of antenna elements, as I mentioned before, over 1,000 of elements is envisioned. Therefore, a cost-effective, highly integrated solution is necessary for this solution. So, and certainly we do not need to, we don't only build one arrays or one sub arrays, but the whole array size needs to be scalable. And just for one example of the possible solutions from different industrial players, including PCME, so, has introduced the beamformer, multi-channel beamformer chips, and also the up-down conversion chips, which work together has to meet the extremely demand of the size and high functionality requirement, which can be packed. And scalable is a keyword I have to emphasize for this large scale deployment or commercial deployment of success, and without compromising the system performance. So without mentioning AI nowadays, it's difficult to end a talk. I would emphasize also even the 3GPP has already started the AI work item studies. In the release 19 and release 20, you can see the official schedules is started exploring AI machine learning to benefit the end-to-end network, meaning at the different layers, the AI machine learning. For example, the waveform design, even the hardware optimizations, and without even mentioning the network deployment, user experience optimizations, AI machine learning would also play a more increased role of benefiting the network quality and efficiency. So with that, I'd like to conclude my talk. As we can see, there is a big chunk of spectrum up to 700 megahertz spectrum in the upper 6 gigaband and potentially more than 2 gigahertz of the spectrum for exclusive use or shared use in this FR3 band, the 7 to 15 gigahertz as the initial primary focus. With a wider bandwidth, channel bandwidth, and a higher number of TRX channels, and a larger antenna active array numbers, these are envisioned to increase the network coverage and capacity and the spectrum efficiency as well at FR3 band. The sustainable design considerations and the trade-offs are really needed at both architectural levels and also at the component levels, as I introduced in the talk. The smaller footprint and high functionality and cost-effective front-end solution are really necessary for this extremely massive MIMO beamforming architectures. The innovation of semiconductor process, active and even passive circuit antenna design, filter design, and packaging